We have an arrangement of 3 particles. We have a proton and 2 electrons as shown in the picture. We'd like to calculate the net force acting on the proton. So the proton is at the lower left corner. There's an electron to the right of the proton, and there's another electron on top with an angle. So I labeled the electrons as E1 and E2, but they're identical. They have the same amount of charge. Basically, we have a force applied by each electron. So electron number 1 is applying force 1 on the picture. Electron 2 is applying force 2 on the picture. Because the electrons are applying a force on the proton, these are attractive forces. So the directions of the forces are as shown on the picture. So there are 2 forces acting on the proton. We want to find the net force. We need to calculate each force separately and add the forces using vector addition to find the net force. In particular, in this problem, we'd like to find the magnitude and direction of the net force. So first we're going to find the components, and then we're going to find the magnitude and the direction of the net force. Now keep in mind that all these 3 particles have the same have the same absolute value of charge. They all have elementary charge E, that's the electron's charge. Obviously, electrons have negative E, protons have positive E, but because we already determined the directions of our forces in our calculations, we're going to use the absolute values of the elementary charge E for each particle. And we're going to apply Coulomb's law to calculate the force, to calculate each force. Let's start with F1. So F1 is a horizontal force. It points to the right. It only has an x component. It's going to be equal to the magnitude F1, which is determined by Coulomb's force, right? K times Q1, Q2 divided by distance squared. In this case, well, K is the Coulomb's constant. Q1 times Q2, we're talking about the proton and the electron. So each one has charge E. E times E, that's E squared. E being, again, the elementary charge. Q times E squared divided by the distance between the 2 squared, which is R. By the way, the distances between each respective electron and the proton are equal. I labeled both of them as R. So K times E squared divided by R squared times I hat is the first force vector F1. Again, E is known, that's 1.60 times 10 to negative 19 Coulomb. Theta is the angle in the picture. We're not using it yet, but it's 65 degrees. Distance R is 1.50 times 10 to negative 10 meters. So if you plug in the numbers for K, and K is also known, it's 8.99 times 10 to 10 to the 9th power. So if you plug in the numbers, here's what you get for F1. Keeping 3 significant figures, 1.02 times 10 to negative 8 newtons I hat, that's F1. So let's calculate F2. F2 is making an angle, so it has an x and a y component. The x component is going to be equal to the magnitude of F2 times cosine theta. The y component is the magnitude of F2 times sine theta. So let's set up our expression for F2. Both components are positive, and the magnitude of F2 is again K times E squared divided by R squared, exactly the same as F1 because the charges are the same, the distances are also the same. But we have an x and a y component. So the x component is the magnitude times cosine theta, theta being 65 degrees, so that's given. I hat, this is the x component, plus K times E squared over r squared sine theta j hat. If you plug in the given numbers and calculate, here's what you get. Zero point 431 I hat plus 0.924 j hat. There's an overall factor of 10 to negative 8 and the unit is Newton. So this is F2. Now let's go ahead and add these two vectors, force vectors together to find the net force. F net is equal to F1 plus F2. So sum of the forces, this is F net, is equal to F1 plus F2. F2. We are going to add these two vectors component by component. So we add the x components together and the y components together, and that gives us the net force. So I have three terms here. The first term 1.02 I hat, that's F1 basically, and the last two terms are F2, 0.431 I hat, that's the x component of F2, 0.924 j hat, that's the y component of F2. Again, I have an overall factor of 10 to negative 8 and the unit is Newton. So we add the I hats together. We only have a single j hat term, so that one remains as is. And the result is 1.45 I hat plus 0.924 j hat times 10 to negative 8 newtons. So this is the net force in terms of its components in unit vector notation. Now let's find the magnitude and the direction angle of this net force. How do I find the magnitude? Let's use the Pythagorean theorem. Basically, the magnitude is equal to the square of the components added together, and then we take the square root. So I have the calculation shown here. I square the x component and square the y component, add the two components together, take the square root. You can see that I left out the overall power of 10 to the 8 and the unit Newton. These are common factors, so they'll be squared and then they'll come out of the square root anyway. So we can actually leave those outside because those are the common factors. When we do this calculation, we get 1.72 times 10 to negative 8 newtons for the magnitude of the net force. Now let's find the direction angle. If you look at the components of our net force, both are positive, so this vector lives in the first quadrant. We're going to calculate the standard angle, in other words, the angle between the vector and the positive x direction. So let me draw a quick sketch here to see what's going on. Here's the x-axis, here's the y-axis. What does my net force vector look like? Again, both of its components are positive, so my vector looks like this, more or less. So if you think about it, the x component is greater than the y component, so the vector is closer to the x-axis, like so. Let me label the axes. This is the x-axis. Here's the y-axis. And the arrow represents my net force vector. I'm going to calculate this angle here. I'm going to call it alpha. So this is the one I'm calculating here. If you think about it, tangent alpha is the y component of the vector divided by the x component. Let me draw some lines here. So this green segment represents the y component of my vector, if you think about it, and this red segment here represents the x component, right? So tangent is opposite divided by adjacent. The y component, the green segment, is the opposite side, and the red one is the adjacent side. So y component divided by the x component is tangent alpha, but alpha is my unknown, so I'm calculating alpha. So I'm going to do an inverse tan. Alpha is equal to inverse tan of the y component of the net force divided by its x component. Now let's plug in the values and calculate. Each component has an overall factor of 10 to negative 8. Those factors, of course, cancel, so no need to put those in your calculator. And when you do this calculation, inverse tan of 0.924 divided by 1.45 is equal to 32.5 degrees. That's alpha, the angle between the net force vector and the positive x-axis. Now, does this make sense? What's the meaning of this value? If you think about it, this is really just half of 65 degrees, right? Which is theta. Is it a coincidence? It's not a coincidence because there's a lot of symmetry in this problem. If we go back to the picture, the two electrons are at the same distance, they have the same charge, so the magnitudes of F1 and F2, as we already saw, are equal. In that case, the net force vector will go through the middle point of the angle theta. If you think about the parallelogram method, the graphical method that we use sometimes to add two vectors, you can imagine that the diagonal that you will draw eventually when you do the parallelogram method will go through the middle of angle theta. So, and here's the final answer.